Hi girls, this is a video for today's class and it's going to take a look at section 1.5 in your textbook, which is all about looking at different types of problems and seeing what types of strategies you can use to get to the final answer for application work. So what you're going to find is that there are 2 pages in this packet that have review. And these are from some of the unique cases that we've talked about in section 1.3 and 1.4, and also some of the application problems that we've seen there. Then we'll go ahead and get into new material where we're really going to take a look and break down different methods for solving application problems. Now you can watch this video with the volume on, and also YouTube has the opportunity for subtitles. So if you prefer just to watch the subtitles, that's certainly great too. And feel free to, if you feel like this material is easy, to try the problems on your own and then come back and check your work using the video. Or on the other hand, if you're feeling like this is a little bit challenging, you can really go slow and rewatch each of the steps as you go along. So the first place we pick up with the warm-up is in special cases of equations. So if we're going to try to solve for x, what do we want to keep our eyes out for? So this is what we saw in our previous quiz, but there are things that we want to keep coming back to, so that way we feel confident throughout the chapter and as our equations may become more complex. So here my goal is to solve for x. Over here on the left, I'm going to distribute that 10. So I'll get 10x minus 80. On the right-hand side, I'm going to combine these two like terms so that I have 9x, and then I have to distribute this negative. So the minus sign applies to the 9 and to the minus x. So this is going to become minus 9 plus x. So then I continue combining like terms. I still have 10x minus 80 on the left, and over on the right-hand side, I'm going to have 10x minus 9. Now, if I subtract this 10x over to the left-hand side, so I do minus 10x minus 10x, those are going to go away. They're just going to cancel out. And I'm left with the expression of negative 80 is equal to negative 9. Now, that's not a true mathematical expression. Those aren't equal. So what I report back is that there are no real solutions. There aren't going to be any numbers that make this expression true. And that's your final answer there. That's one of the special cases we can come across with equations. Then we have another option. Number 2 also says to solve the following equation for x. So I'm going to go ahead and distribute this 3 in here, and we'll get 18x minus 9 is equal to, here, I'm just adding what's in parentheses, so I'm going to combine this 2x and this 16x, and I'll get 18x. And then I have 18 minus 27. So if I have 18 minus 27, I end up with minus 9 over here on the right. Because everything on the left is equal to everything on the right, when I go to combine like terms, so I'm subtracting the negative 18x, those values will cancel, and I'm left with negative 9 is equal to negative 9. Now that's a mathematically true statement, but what that tells me is I'm not solving for a specific x value because any x value will make this equation true. So I can say all real numbers, or another way that it would be okay to say this is infinitely many solutions. And there's infinitely many because any x we plug in will work. That would be our final answer there. So we're good with no solutions, and we're good with all real number solutions. Then on problem number 3 on this warm-up, this is another fraction problem, and I want to keep coming back to the fractions because they come up in every different kind of equation that you'll see. So we'll talk about quadratics, we'll talk about cubics, we'll talk about some funky equations that you might not have seen before. And every time we come across one of those, we want to be able to know what do we do to work with the fraction. So we'll keep getting in practice with these. So anytime I have a fraction where there is parentheses around values, it's a good idea to go ahead and start off with distribution. So here I have 3/5 x minus 9, and I'm going to go ahead and distribute this guy in. So I'll have 2/7 x minus, remember with fractions we multiply straight across up top and straight across down below. Now looking at this kind of fractional expression, I'm going to use the clearing fractions method. So when I go to clear a fraction, I want to think about the fact that my denominators are 14, 7, and 5. So I need to think, what number are all three of these values divisible into? Now, if I have 14 times 5, then remember, you can always check things on your calculator too. 14 times 5 is going to give you 70. 7 is also divisible into 70, so that can be the common denominator that we use. We may end up with some bigger values, but that's okay. So I'm going to multiply everything on this side by 70 over 1, and everything on this side by 70 over 1 as well. Then I just have fraction multiplication. If I first distribute here, let me grab a different pen. Going into that first term, I'll end up with 210 over 5x minus, if I have 70 times 9, that's going to give me 630. Now, looking at this, I've got 70, and that one's going to apply over here first. Well, I'll end up with 140 over 7x. Minus, up top here, I've got 140 over 14. So now I just have to do some simplification. If you do 210 and divide that by 5, you'll get 42. So I have 42x minus 630 is equal to, I've got 140 divided by 7, so that's going to give me 20x, minus 140 divided by 14 is going to give me 10. Now, I'm running a little bit out of room here, but I'm going to go ahead and combine like terms, and then I'll just move up to the next line. So I'm going to subtract 20x from both sides. When I do that, this 42 minus 20x, it's going to move up here, will give me 22x minus 630 is equal to negative 10. I can add 630 to both sides, so I'll have 22x is equal to positive 620. I can divide both sides by 22, and x is going to be equal to 620 divided by 22. Now, both of those numbers are divisible by 2, so if I divide 620 by 2, I'll end up with 310, and that's going to be 310 over 11. And that's our final answer for x. So if we want to keep it as a fraction, that's as far as we're going to go. We can't reduce any further at that point. So those are the types of equations we want to feel comfortable with from section 1.3. Now we want to talk about some application problems with section 1.3 and 1.4. So let's check out this application problem. It's really similar to one of the ones that you saw in your study guide from this last quiz. So it says, in the past, phone companies would package their products to make them more attractive to potential users based on the number of minutes used. So back when I had cell phones in high school, you paid per minute. So if you wanted to talk to your friends, you could only call at certain times of the day because you would use less minutes in the afternoon and things like that. So it's kind of nice that you don't have to worry about that anymore. This says if a potential customer talked on the phone for 350 minutes in 1 month, which of the following would be a better deal? And then at how many minutes of usage are these plans equal? So the idea is that you're trying to decide between two different phones to figure out which one's going to be less expensive based off of the amount of talking you do. So it says package A includes a free phone and 300 minutes. It will cost 12 cents per minute for each minute over the planned time. Package A has a base rate of $39.95. So let's think about package A for just a second. If I'm trying to figure out how much plan A is going to cost in 1 month, I don't have any charge for the phone, so I don't have to worry about that. What I do have to worry about is this base rate of $39.95. So I have to pay $39.95, and then it says 12 cents per minute for each minute over the planned time. So in this case, I can describe that by saying 12 times x minus 300, because that's going to calculate however much more you talk than 300. Then it says package B has a phone that costs $10 and has 350 minutes of time and 8 cents per minute for each minute over the planned time. Package B has a base rate of $35.95, not including the phone. So the first month that you have plan B, your cost is going to be the original $10 that you spend on the phone and this base rate of $35.95. So no matter what, in that first month, you're spending $45.95. And then it says 8 cents per minute over the plan time. So in this case, it has 350 minutes of time. So we will call this 0.08 times x minus 350. So in the first month, if we're trying to figure out which one is going to be cheaper, all we have to do is plug in the 350 minutes we're planning to talk on the phone. So right in here, I'm going to plug in, so I've got $39.95 plus 12 times 350 minus 300. Now that whole expression is one that I can easily plug into my calculator. So I can say $39.95 plus 12 times 350 minus 300. And the result that I get is $45.95. So that's how much I'm paying here. Okay, then I want to take a look at package B. So when I plug in for 350, in this case, my second term is going to go away entirely. So I'm going to have 350 minus 350. This whole term is going to go to 0, which means that I'm also just going to end up with $45.95 here. So originally I was trying to figure out which one's a better deal. Well, for each of these phones, you're going to be paying the same. So neither one is a better deal. They would cost you the same amount. That means that we don't have to solve for the second part of the question, because that says at how many minutes of usage are these plans equal, and that's just the 350 minutes that this customer would talk. If for some reason we found that these were not equal, and then we were asked to solve when they were, all we would need to do is to set these two equations equal to one another and solve for x. If we did that at this point, we would get 350, because that's when you get the same value out when you're talking the same amount of minutes on each plan. Last up on the warm-up, we've got some review of getting single variables by themselves. So let's take a look at what that might appear like in a science class, and then we'll see what that's going to look like in an algebra class. And this is your last set of problems from the warm-up. So, number 5 says, given the following equation from physics that describes the total momentum in a system, solve for the momentum value of one object described by the variable m1. So, in physics, the quantity of momentum is your mass multiplied by your velocity. So if you think about a car, this is my artistic rendering of a car, and a car moves with some speed, which we call velocity. So mass is very similar to your weight, and the mass of a car, let's say, could be 1,000 kilograms. So when you multiply 1,000 kilograms by how fast you're going, that quantity of speed and mass multiplied together is that momentum. And if you have more than one object moving in a system, then you would add the momentums together. So that's something you might learn about in science. What you want to pay attention to in algebra is that if you're given expressions like this, you can always solve for a single variable. So here, my goal is to get this m1 by itself. So these two terms don't have an m1 in them. So I'm just going to subtract it over to the other side. I'll have total momentum minus mass 2 times velocity 2 is equal to mass 1 times velocity 1. At that point, m1 is almost by itself. I just have to undo the multiplication over here on the right-hand side. And I'm left with an expression that describes just m1 over here on the right. So m1 is equal to mass minus m2 v2 all over v1. And that's your final answer there. Again, one of the things that we saw before is that I could divide these expressions and write them out as separate fractions, but I'm also okay to leave it as one numerator over one denominator, and that might be easier to plug in. All right, this next one looks like there's a lot going on, but I promise it's not that hard. For number 6, it just says, given the following algebraic equation, solve for the variable y. This means you're going to isolate y on a single side. So I've got these expressions. I've got a term without variables, an x, a y, an xy, and a zy. So, like we talked about yesterday, my goal is to bring all of the terms that have a y in them over to one side. So in this case, I'm going to go ahead and add the 6y here over on the right. So I'll have 3 plus 3x is equal to 4xy plus 6zy plus 6y. Okay, so now everything on the right has a y, everything on the left does not. So what I want to do at this point is to go ahead and pull that y out in front and rewrite this expression with parentheses. Now all I have to rewrite in parentheses is what I would multiply this term by to get back to this expression. So I'll have 4x for my first term, 6z for my second term, and then 6 for my last term. Now, what's going on in between the y and the parentheses is really multiplication. So that means to undo multiplication and get y by itself, I'm just going to divide by this whole bulky thing, 4x plus 6z plus 6, and it's going to cancel out on this side. Then I'm going to do the same thing over here, 4x plus 6z plus 6. Well, now all of a sudden y is by itself. I've fully isolated it on one side, and I have an expression that has y on one side and no y values on the other. If you wanted to rewrite that just so it looks clean, we'd say y equals 3 plus 3x all over 4x plus 6z plus 6. And that would be your final answer. All right, you guys, so now we've got some new material to get into. We just have some problem-solving strategies to discuss, and we'll see how they look in different application problems. All of these problems are pretty easy. It's just the setup that involves a little bit more thought. So we have 3 different strategies that we'll look at. One is going to be solving equations where you know the formula really well that's involved. One is going to involve looking at patterns, and one's going to involve drawing pictures. So the first equation that we want to be really familiar with these kinds of application problems is the distance equals rate times time formula. So you might have seen that in a previous science class or previous math class, but all that this says is how far you've traveled, your distance, is equal to the rate or speed that you're going, and how long you went that speed. So let's see some basic ones and then we'll get a little bit more involved. First example says you're taking a train from Barcelona to Madrid, and the train travels for 390 miles. If your trip takes 3.51 hours, what is the train's speed? Its rate. So all we have to do is say distance is equal to rate times time. That's this value d, r, t. But I'm trying to solve for the rate. So I'm going to divide both sides by t here, and I can say that rate is equal to distance over time. So I'm going to take the distance value of 390 miles and divide by the time value of 3.51 hours. When I plug that into my calculator, 390 divided by 3.51, I get 111.11. So I can write that out, 111.11. I'm just going to use 2 decimal places, miles per hour. So that's my speed. Now let's check out another application problem. It's going to use the same equation, slightly different setup. Example B says a submarine travels from a port on Oahu to a port on Maui. So it's just going between Hawaiian islands. The trip there takes 3 hours, and the trip back takes 5 hours. If the average speed on the return trip was 33 miles an hour, what was the average speed on the trip there? So what we want to think about is that this submarine is starting on Oahu, going to Maui, so it's making the trip there, and then it's turning around and it makes the trip back. So anytime we go from Oahu to Maui, and Maui back to Oahu, the distances are the same. So the distance that I traveled one direction is the same as my return distance. So if I'm trying to figure out information about what's happening on one leg of the trip and one leg of the other leg of the trip, I can always just say that the distance the first time is equal to the distance the second time. How far apart they are isn't changing. Now, we just said up above that distance is equal to rate times time. So my rate on the way there times my time on the way there is equal to my rate on the way back times my time on the way back. And I'm trying to find the average speed on the trip there. So I'm trying to figure out this rate here. That's my dog barking in the background if you can hear her. So I just need to plug in the values that I have to solve for the value that I don't have. If I want to go ahead and set this up as an equation where I'm just dealing with rate on one side, I can divide the time over to this side, and I'll say my rate on the way there is equal to my rate on the way back times my time on the way back divided by my time on the way there. And then I'm just plugging in values. So my rate on the return trip was 33 miles an hour. My time on that return trip was 5 hours. My time on the first trip was 3 hours. So I've got units here, miles an hour, hours, and hours. And I can just go ahead and plug that in. 33 times 5 is 165. Divided by 3 gives me 55. So my rate on the way there was 55 miles an hour. All right, we've got one more distance, rate, and time problem to try. This one says, a car left New York City traveling towards Hilton Head, South Carolina. A faster driver left New York City 3 hours later at a rate of 80 miles an hour and caught up to the first car after 6 hours of traveling. What was the speed of the first car? Okay, so we have a car and they leave from New York traveling down south to Hilton Head. A little while later, another car leaves, and then after a certain amount of time, it catches up to that car. When the two cars are caught up to one another, that means they've traveled the same distance. So just like up here, where I had a same trip down and back, or there and back, here I have one car travel a distance, and the other car is traveling the same distance. So I can again say the distance of the first car is equal to the distance of the second car, which means that the rate of the first car times the time the first car has been traveling is equal to the rate of the second car times the time the second car has been traveling. Now, once again, I'm solving for the speed of the first car, which is still R1, just like it was up here. So, in this case, I'm going to go ahead and keep these guys separate from here because I want you to see what we're specifically going to plug in. We know that our first car left New York City. The second car left, and when the second car left, they were traveling 80 miles an hour. So I'm going to plug in 80 miles an hour for the rate of the second car. Then we want to think about time. Our first car left, then the second car left 3 hours later, and the second car left after it had been traveling for 6 hours. So our second car was traveling for 6 hours. If the second car left 3 hours before, or 3 hours after the first car, that means the first car has been traveling for 3 hours longer. So if the first car has been traveling 3 hours more than 6 hours, we know that it's been traveling for 9 hours. And we're solving for the rate of that first car. So to get R1 by itself here, I just divide by 9 hours. And I divide by 9 hours over here as well. So again, I'll go ahead and plug in here. 80 miles an hour, traveling for 6 hours. Divided that by 9. So that means the speed of my first car is going to be 53.33 miles an hour. There are a lot of different ways that these kinds of problems can be phrased. But no matter what, all you're doing is working with distances and setting different distances equal to one another or to a specific value. And then you're solving for a rate and a time. We've got 2 more categories of equation solving strategies. The next one I think is probably the easiest one. And it's one that you start out using with basic equations, and then as you get to more complex equations, you're just looking for different, more interesting patterns too. So here in this scenario, it says a hot air balloon is floating in the air attached to a tether. So we've got a balloon, it's just hanging out, attached down to some kind of tether on the ground. Then the tether is released and the operator begins timing the flight. The height of the balloon at various points in time in minutes is given below. So my balloon starts out right before we begin timing, and it's already at 100 feet in the air. Then what we see is in different increments of time, we have different heights that are resulting. So I can go ahead and come up with an expression that describes the height of my balloon as a function of time or measured over time. So I can say that height is equal to the original value, 100. That's where it's starting. And then somehow it's changing at a specific rate over time. So what I want to investigate is what pattern is occurring between these values. So I start at 100 feet. 5 minutes later, I'm at 1,200 feet. So that means in this interval, I've gone 1,100 feet. Then 5 more minutes pass. And so after 5 more minutes pass, then I go up 1,100 feet as well. And then another 5 minutes pass and I go up 1,100 feet again. So every 5 minutes, I'm going up 1,100 feet. So I can say that I'm being lifted at a rate of 1,100 feet every 5 minutes in the air balloon. And if we were to divide that out, 1,100 feet every 5 minutes is the same thing as 220 feet per minute. So my rate value here is 220 feet per minute. So I can say my height is equal to 100 plus 220 times time, where time is the number of minutes that have passed. So again, starting at 100, every minute that passes, I go up 220 feet. And I figured out how much I'm going up each minute by looking at, after every 5-minute interval, how many feet did I go up in the air. So I can use that information where I'm analyzing patterns to figure out a rate to come up with information about either the height value or the time value. So this question says, how much time will have passed when the balloon reaches 4,000 feet? So I'm just going to plug 4,000 feet in for my height. And then I'm going to solve for my time. So I've got 100 plus 220t. My only goal here is to get t by itself. And so I'll do that first by subtracting 100 from each side. When I subtract 100 from each side, I'm going to end up with 3,900 is equal to 220 times time. I want to get time by itself, so I'm going to divide both sides by 220, divide by 220 over here. And I can plug in and see that if I take 3,900 and divide by 220, I've got 17.73 minutes if I round. So my time is 17.73 minutes. So after that length of time, my hot air balloon is at 4,000 feet in the air. We have one more strategy and then we are done for the day with new material. This strategy I think is the easiest. It's just if you come across information that describes a picture, go ahead and draw a picture and see what you can figure out algebraically. So this says Mrs. Alt is interested in putting up math posters in her classroom, and I always am. It tells me one classroom wall is 30 feet in length. She has 3 posters, each of which is 6 feet in length. She wants the spacing between the posters to be equal, and to have the distance between the posters and the walls on each side twice the space of the distance between the posters. So let's get this all in a picture. I'm going to go ahead and draw the 30-foot wall that's in the classroom. So this is 30 feet. So I'm good to go there. Took care of that piece of information. Then it says I have 3 posters, each of which is 6 feet in length. So I'm going to go ahead and draw in 3 posters. Got 1, 2, 3 posters. And these guys are all 6 feet. 6 feet and 6 feet. So I took care of that piece of information. It says I want the spacing between my posters to be equal. But it doesn't tell you what we want that spacing to be. So if we have a quantity that we want to work with, but we don't know what numerical value it has, we can just call it x. So I'm going to call this x and this x. So that takes care of the spacing. And then it says we want to have the distance between the posters and the wall on each side twice the space of the distance between the posters. Well, I don't know the space of the distance between the posters, but I can say 2 times that space by just saying 2x over here, 2x over here. So if I add 2x plus 6 plus x plus 6 plus x plus 6 plus 2x, I need to get to 30 feet. And that's going to be easy. So 2x plus 6 plus x plus 6 plus x plus 6 plus 2x is equal to 30. I'm going to go ahead and combine like terms here. So I've got 2x plus x is 3x, plus another x is 4x, plus 2x, that's going to give me 6x. That took care of all my x terms. Those are going to go away. And I've got 6 plus 6 plus 6, which is 18. So I have 6x plus 18 equals 30. I'll subtract 18 from both sides. When I do that, I'll have 6x is equal to 12. And then I'll go ahead and divide both sides by 6. So 12 divided by 6 is going to be 2, and we're measuring in feet. So each of the spacings between the posters is going to be 2 feet. So this guy will be 2 feet, and this guy will be 2 feet. These are each 2 times 2 feet, so this value is going to be 4 feet, and so is this value. If you ever want to check to make sure you solved correctly, you can always just go back and add up each of these values and check to make sure that it's the total length that you're working with. So you're just drawing a picture, filling in the values that you know, and assigning variables to the values you don't, so you can figure out whatever spacing is involved. So those are your 3 different categories of problems that you'll be asked to try tonight. You have ones where you're setting up a picture. Then you have ones where you're working with some kind of trend to figure out a pattern. You've got some that have distance, rate, and time. And then again, our warm-up just covered some previous material, so that way we feel prepared, connecting all of our concepts moving forward. At this point in time, go ahead and try your 1.5 homework. A lot of problems from that homework are easier than the ones that I just went over, so my hope is that it's a pretty doable one to finish, and that after the welcome picnic tomorrow, you won't have any math homework that you're still working on, that you can finish it all tonight. So please email me if you have any questions, or just call me over in whatever remaining time we have in class. Thank you guys, and have a great weekend.